Okay, thank you very much. I understand I have 25 minutes, so I will be late. Okay. So let's skip it. What I would like to tell you, I would like to start with 3 motivating examples and try to convince you that pattern matching can be useful for solving all of them, and actually combinatorial calculus, analytic techniques, information theory can actually help us to extract some information knowledge. So in the first example, the simplest one, you have DNA or any other biological sequence. And this sequence is very interesting. It has many different regions. For example, there are some regions, the red one, that genes reside. There are some others, transcript start, where the promoting area that tells you something interesting coming in. There is intron that has some other job to do. And you would like to learn something about the sequence, how you can do it. You take a small word, a special one, and you prop this sequence, and you are counting the number of occurrences of this word. And it turns out that in different regions, you might have different occurrences. I call it exact string matching problem. I'm counting the number of occurrences of a given word, or maybe a set of words, and this tells me something about the underlying text. In another example, which is Google, it's a completely different problem, but pattern matching still can be useful. Here, I put 3 or 5 keywords, and I'm looking for web pages that contain them. Here, it's interesting. First of all, these words will be right now symbols of a bigger alphabet. And you can see that they appear in bold, but these words appear in these web pages not consecutively, like I did it here, like a string, but rather as a subsequence. It means they appear with a gap. Okay? And if I would like to rank these web pages from, let's say, from the point of view of the most interesting or the p-value, I need to understand the number of occurrences of these keywords as subsequences. And the gap between them do matter. By the way, if you want to find the word Szpankowski in Hamlet, you won't find it as a string, but you find it as a subsequence with gaps about 14 symbols between each symbol. Okay? So randomness makes funny things, and we have to somehow make sure that when the sequence or string becomes significant, and that's why the analysis of that kind of thing as a subsequent analysis does matter. Finally, Twitter. If I take 2 Twitters, I would like to know automatically whether they talk about the same or not. So how can I do it? In general, I take 2 strings, and I want to know how close they are. And the way to do it, I will count the number of common subwords. How many subwords here and here are the same? And I count the number. And if I do it, I can say that 2 strings are closer to each other if the number of common subwords are bigger than in another case. And then I can use it actually to classify all Twitter sports, politics, science, and so on and so on. The problem that I need here is string complexity, which is defined as for 1 word, the number of distinct subwords. For 2 words, this is called joint string complexity, the number of common words. So these are 3 examples from a bigger area that I call pattern matching problems. And there are several of them, and I would like, let me give you a little general definition first and what it is about. So given a word and a text, and a text, let it be of length n, and usually text is generated randomly, but not always, and a word could be a word of length m or a set of words. Okay? The basic question that I will be interested in, because this will tell me a lot about the text, I will be counting the number of occurrences of this word, a set of words and maybe subsequences in a bigger text. And this is my parameter that I'm interested in. And then you can define different pattern matching problem. One of them is the basic one, exact pattern matching, that I have one string, and I count the number of occurrences of such a string in a usually randomly generated text, memoryless Markov or something else. General string matching is actually much more interesting. Now I have a set of words. I have a special word, I call it W0, which is a set of words, and each of this is also a set of words, but then I call W0 a forbidden set, and here what I might be interested in general, I'm interested in occurrences of all words, the red one, W1, WD, in a text in which no word from W0 does occur. So this is a forbidden word. And actually, when this is 0, this is called generalized pattern matching. If it is non-empty, then I have, under the condition that non-pattern from W0 occur. I might have all of them, by the way, empty, and then I'm looking for a text in which none on W0 occurs too. And this is a constrained pattern matching, okay? More, and this is the most general that we consider, subsequence pattern matching. Now I have a word, maybe a set of words, but now I'm looking at occurrences of this word at a subsequence. So with my occurrent position, I1 or I2 or IM. And there is a gap between them. And I might consider a lot of different things. I might assume that the gap is bounded by some numbers, and I might assume that some symbols have to be within bounded region and some not, which is if all of them, the gaps are unbounded, I call it unconstrained pattern matching. So for example, the word date does not occur in hidden pattern, but occur as a string, but as a subsequence, as you can see it. So this string pattern matching sometimes is called hidden pattern matching. And finally, in lamp-as-if and other kind of things, what you do actually, your pattern is the part of the text. Let's call it self-repeated pattern, but doesn't matter. Okay, so I hope I convince you that there are a lot of interesting stuff going on there, and you need a collection on all of them in one place and techniques to analyze it. And I want to deliver this to you. So we are just finishing with my friend Philip a book. It should appear maybe in June, July, maybe be on display in ISIT. This is called Analytic Pattern Matching from DNA to Twitter. I try to give a motivation from both of them, different ideas and different techniques being used. And actually, here what it is, so what we talk then, exact string pattern matching, and I will give you an example how we do make analysis, trying to explain to you analytic here. The constraint pattern matching is for decay codes when the text has some constraint that, for example, 0 has to be separated by 1, so it doesn't matter, or something more general. General string matching is a very interesting problem. I explained to it, you have a set of words and maybe a set of forbidden words, and you try to understand how many of them occur. The problem is that the set of words might be very dependent. Some of these words might be part of the other words, and how to analyze it. And the subsequent, so the first part of the book explain basically, present analytical tools from complex analysis, and you are not surprised about this, and trying to predict probabilistic behavior. And I give you an example in a second. The second part of the book is basically application. So we start with digital trees, Patricia tried digital third tree, when you have set of independent strings, and you build a tree, digital tree, and you would like to understand profile of such a tree. How many nodes do you have on level L? What is the path length from the root to a leaf, and so on and so on. You are much more interested in this one because suffix tree is what we are using in Analytic 77. Now you have one big string, and you take suffixes and you put it in a digital tree, and you try to understand it. What we are proving, and we proved it many years ago, but we put it here, is that the random tries are coming from digital tree from the word retrieval. Random tries resemble suffix trees, so whatever technique I have here can be used here. This is much harder to analyze. Analytic 78, we right now have a limited distribution for redundancy of Analytic 78. As you remember, it was an open problem for a long time. And string complexity is something new that we did with Philip. With Twitter application, when you have two strings, they are looking for the number of common subwords. Okay, so this is, if you are interested, that's what is there. What I would like to do right now, I would like to give you an example of an analysis and try to show you how we're actually approaching it. The two main tools that we're using are combinatorial calculus and analytic method. By analytic method, I mean method of complex analysis applied to discrete problems. This is what the group analysis of algorithms is doing for last few years. So I remind you what I'm going to talk only about chapter 1, exact string matching, the simplest case. And I want to tell you how we can do the analysis. So I have one word, I have a text. Text generated by memoryless. Markov can be handled not much more complicated. And I'm trying to understand the number of occurrences of the word W. W is given. Text pattern is given in a random text. Symbolic calculus and analytic tools. So to know, nobody's surprised, no one's surprised, we're using generating function of a language. A language is a collection of words. So here it is defined. Z is a dummy parameter. When I will go from combinatorial calculus to analytical tools to extract asymptotics, I will make Z complex. But right now it's a dummy parameter. It's basically you take all words from the language, you multiply, you weight it by probability, and you raise Z to the length of the words. Why is it interesting? Because if I have collection of two languages, or two languages, and I concatenate them, what does it mean concatenate? That I take a word from one language, and I take another word and concatenate it. Generating function do multiply. And that's the whole thing. So a complicated convolutions and behavior becomes basically algebraic equation. So there is one language that is very important, and I cannot go anywhere without explaining this. So if you have a pattern like, so this is my pattern, W, A, B, C, A, B. This pattern has a structure. When I say occurrences, I mean that the pattern can overlap when they do occur. Notice that here, if I shift this pattern, the first two symbols and the last two symbols are the same. So when I shift them, I have, you can see that these two do overlap, and the most interesting part of the pattern is what is here. And I call the set S. So in general, when I have a pattern, and the first K symbols are the same as the last K symbols, which means when I shift it by M minus K, I mean the length of the pattern, the last overlap with the first. So I have two occurrences. And the word starting from here, from K plus 1, K is this here, is this set of these words are very important. This is called autocorrelation set. I define generating function like this, and here I have an example where here when I have a pattern BAB, my set is empty word and AB, and this value K's are 1 and 3. Okay, this is a generating function. Okay. Now I have to explain this one to you. So I want to generate a language, let's say T4, which will be the set of all words that have exactly 4 occurrences of the word W, which W is given to me. Let's say W is A, B, A. So I want all words that have exactly 4 occurrences of W. I will introduce to you 3 languages. And you. Language R contains all words such that W occurs only once at the end of this word. So here, if I have word ABA, I don't have a good example here, so I give you later an example. Here's an example that the word in red is basically occurs only at the end. Word M, set of words M is a little different. So let's U belongs to this language. Now, when I take U and concatenate the word W from it, I want exactly 2 occurrences. So here's a good example. I have a word BA, and my alpha and my pattern is ABA. When I concatenate ABA to BA, what do I have? I have 1 occurrence here and another occurrence here. So W language is such, M language is such that when I concatenate W to a set, to a word from M, there are exactly 2 occurrences. Exactly 2 occurrences. And finally, I have ultimate set such that U does not have any occurrences of W, but if I concatenate with W, I have exactly 1. So look what I can do right now. How I can create language with 4 occurrences. I take a word from language R. It has exactly 1 occurrences of W here. Then I take a word from language M. It has occurrences at the end, but if I concatenate the word W from previous R, I have exactly 2. I know that up to here, I have exactly 2 occurrences of W. Then I take another language M, and finish with U. Let's count. How many occurrences do I have? 1, 2, 3, 4. So here is the funny thing, that the language that contains exactly R occurrences of the word W is basically concatenation of language R, R minus 1 concatenation of M and U. So if I tell you how to construct the 3 languages, I can basically give you a construction of T of R, something that I'm interested in. And these are basically a relation between sets. Let's look at this relation. I don't have much time, but let's look at this one. So I'm taking a word from language U. Language U is the one that has only no occurrences unless it's on the left. If I add a symbol, 1 more symbol from the alphabet, what can happen? Maybe W does occur, so then it belongs to language M, or it doesn't occur, but it is not anymore empty, so I have to say U minus A. Now, it is very easy to translate this in terms of generating function, because generating function of this Z, M, U minus 1. If I do it, I have basically a system of equations for sets. And if I put random generating function there, random text, then I get generating function, which basically gives me a relation between language M, U, and Z. And you remember what I told you about T sub R? T sub R, this language, was R times R minus 1 times U. So the generating function of this is basically R of Z times R to the power minus 1 of Z times U of Z. And I know how to compute them from this one, so I get everything I want. Okay? I understand I have 7 minutes, correct? Good. So once I have this one, now I'm going from combinatorics to analytic tools. And so I'm going to quickly show you a few things that we can get. You can get a mean is trivial. Variant is not trivial because the autocorrelation set occurred there. I can tell you probability that there are exactly 5 occurrences. I can give you pretty precise central limit law as well as large deviation. Okay, let's leave it there. Believe me, we can get it and did it in the book. I want to show you one non-trivial example of this, that we have to go from chapter 1 to chapter 4 from exact string matching to general string matching. So what's happened, and this is true in many cases, that I'm looking for occurrences of word W1 and also occurrences of another word, W2. So if I have a word and I take any subword of it, this subword, if the original word occurs very often, then the subword must occur very often, obviously. But I would like to know whether the subword of a very frequent word is also significant or not. I cannot look at the number of occurrences. This is not a subword, but very close to this one. I cannot decide significance of occurrences of this based on this word itself if I know that this is significant, because this threshold for significance will be completely different. So I have to consider occurrences of W1 and W together, and actually base my significance level based on the conditional entropy, assuming that the word W is very frequent. What is the average of the occurrence of W? Okay, and it turns out we know it will be a function of n. It grows linearly, but this constant is very different, and to computing it is not easy. You actually have to use tools that we develop in generalized pattern matching, the Bruin graph or some others thing that will allow you to compute it. Why is it important? Here's an example from Denis and Renier. So they probe. So there was a paper that trying to count the occurrences of some string. Here it is, and also strings that are close to it. So this is the original string. There are strings very close to it because of mutation and so on. You have to assume that sometimes this might be mutated into something very close. So this part of this table is what biologists would do. They basically take all of this words, count the number of occurrences, and compute z-score. Z-score is basically the difference between the mean divided by the variance, as you know. And let's look at this word. It's very close to this one. It occurs a lot. Its rank is number 5. If I consider this word without any reference to this one, but if you consider the method that I show you, that the threshold actually is based on the fact that it's very frequent, this word from rank 5 becomes rank 4,000. So because you have to shift it, in order for this word to be significant, it cannot come from the fact that this is frequent. You have to count from something else. It has to be way above this threshold or just occurring this one. So, and this technique allows you to do things like this and get you the central limit result if it's necessary, or any distribution that occurs in application of pattern matching from exact to subsequent pattern matching. Let me finish. I'm sure you're ready for lunch. So I'm done.
So just want to make sure I understand. So your method is used in that application. It's basically used to compute the p-value under the null hypothesis of random string, is that right? So you're trying to say that is there some information, some non-randomness in the string, and you're trying to calculate a p-value based on the null hypothesis? Is that where your techniques are used?
So here's another way to ask the same question. I'm probing a database, and I'm getting some answer. And then I have another query to the database, and I'm getting another answer. I want to know how this new answer, how much more information this new answer actually tells me about the database. And the tool that we have there, can you give you one of the possible answers? So this is this conditional. Exactly. Exactly. And this, because it is general, and because of the analytical tools, if analyticals apply, they gives you extremely precise analysis. You can ask Stefan and the French group, because they do it all the time. That's what Philippe Flageolet, our friend, actually taught us, how to actually apply the analytic tools to combinatorics. So discrete problems are being solved by complex analysis tools.
Thank the speaker.
Thank you.